Welcome. So, previously we learned about two different types of aquifer, unconfined and confined aquifers. In this lesson, we will continue learning more about the difference between these two aquifers. So, in the previous lesson, we learned that confined aquifer has uh, a basometric surface, while unconfined aquifer has a water table. So that was one difference in their property. But in this video, we will learn about another difference in their property, which is their storage. Because uh, remember, the water table means what? Means that like, the pressure where the water sit is at the atmospheric pressure, the top of the aquifer. And when you start pumping water out, what will happen is that you will lower the surface and you will dewater the actual pore space. Versus unconfined aquifer, you have a basometric surface. So water is stored by compression. That's the main storage mechanism. The water is compressed, like water is compressed on the top of one another. So when you start pumping water, you release compressed water, and the water surface will not change. You will not de-water the aquifer, the pore space. The pore space will remain saturated. The water surface will remain. The water level in the aquifer will remain the same. So that's we learned this already in the previous lesson. So there is nothing new here. The new part here is that we will look at this more not qualitatively but more quantitatively. Like we try to quantify this with some equations. Yeah, that's the new part. But okay, again, that's your social media exercise for this week. Yeah, same as other week, but just about this lesson. Yeah. Let's go here. So by the end of this lesson, you should be able to define different storage coefficients. So storativity and specific storage. I know like this course has a lot of term like specific yield, specific storativity, specific storage. Yeah, here it comes, like specific yield, like you will be able to explain like specific yield. Basically, you'll be able to explain like these three terms, like what is the storativity? Storativity, this is like storage coefficient, and then the specific storage and the specific yield. These would be specific yield. This is how much water you can drain by gravity. Yeah. And the specific storage, you will learn how this is related to confined aquifer. So this would be mainly like storativity. It composed on the specific storage and specific yield, and this is specific storage is more pertain to confined aquifer, and specific yield is more pertain to unconfined aquifer, as we will learn. So you'll be able to differentiate the storage in confined and unconfined aquifer. So that's basically the objective of this lesson. So let's look here at what we have. So storage coefficient or storativity here, like this guy, storage coefficient and storativity. Let me just read this from the slide. So storage coefficient or storativity, what is this dimension? It is dimensionless. It is the water volume. So read this carefully, like listen to, don't read it, like just listen to me. Uh, it's yeah, just water volume released from or taking into storage. So that's the water volume released from or taking into storage. So you have like storage, and this is the water volume. So you have volume per unit surface area of the aquifer per unit change in head. So what is this? So here we have, yeah, so this is water volume released or taken from storage, like delta, like how much water you released or you removed from the aquifer from a unit area per unit change in head. So remember, let's see here. Let's look at our, let me get some color, blue color, yeah, or any color. So change in storage, like this is a volume. So this is, oops, this is a change in volume. So this is will have the dimension of L, yeah. What is this? This is area. So this has a dimension of L square, and this is head. Remember, head has a dimension of length. So you get, yeah. Oh, it's here already. So you got like, so this will be like dimensionless. Okay. Or you can also write it like this, like L cube over L cube. Yeah. So that you know that this is volume over volume. So this is basically like how much volume, like in this from a given surface area, like let's say here, like this is like let's consume, this is my aquifer, yeah. Okay, so and this is like your surface area, yeah. So this is like your area. So basically it tells me how much water will get released. So let's say I will release this amount of water, yeah. Maybe that would be the volume of water, yeah. So I will like release this volume of water from this area, giving like some like drop in head, like delta H, some drop in head. Yeah, that will be the amount of water that would be released. Okay, so this is what, like this is a storage coefficient or storativity. So storage coefficient is equal to what? Now this is the interesting part. So storage coefficient or storativity, like S, yeah, is equal to two things. It's equal to aquifer thickness times specific storage and specific yield. Okay, so what does this mean? So the aquifer, the storage in any aquifer, whether like confined or unconfined, uh, it has two components. It has a specific yield. So this specific yield, that's easy. This is how much water we can drain by gravity. So remember, like I told you, let's say I have a column here filled with some gravels, yeah, and then I have a screen here. I open the screen and let water drop. So water will eventually drop. Most of the water will drop other than the water that is like in dead end pore, that's trapped in dead end pore, or the water that is trapped on the surface due to surface tension. Yeah, they will film like if you this is like if this is like your clay particle, not sorry, like your sand or gravel particle, some water will stick on the surface of this particle. It would be like 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 thin film, like you would find like a thin film due to surface tension. So any like, and then other water would be like in a dead end pore. So like you have a particle here, and you have a particle here, you have a particle here, you have a particle here. This is called like a dead end pore, for example, where the water will not be. So this is a specific yield. So this is how much I can and guess what? Like if my water level is here and I allow it to drain, after maybe 1 hour the water level will be here. After 2 hours the water level will be here. After 3 hours the water level will be here. So after, I don't know, certain numbers of hours, I'll be able to drain my borehole, like de-water my aquifer. So this will not be fully saturated. This will be just particles like your sediments or your aquifer material and air, like two-phase air and solid phase and air phase, but there will be no water. This is specific yield, and you can guess that this specific yield would be mainly related to what? To unconfined aquifer. Because in the unconfined aquifer, this is where I can like empty the aquifer, drain the pore space. What is this one? Specific storage. This is related to how much water is compressed. So remember, I told you the main mechanism where you release water from a confined aquifer is that water, you don't like the water level will not change. So like once you pull water out of this, the water level will not change. What will change would be your piezometric surface. Yeah. So specific storage, this has to do with how much water you get out from compression, and specific storage you can see that it will not have Can you like guess what would be like the unit of like specific storage? Uh, like this is has like this is an aquifer thickness, yeah. So this is an aquifer thickness. So can you guess what would be the unit of a specific storage? Because remember, this is dimensionless. So this is dimensionless, and this has a dimension. The aquifer thickness has a dimension of L. And for this to be dimensionally homogeneous, it needs to have a dimension of what? Like 1 over L. Because 1 over L will go with this, and then this will become also dimensionless. And specific yield, we know this is volume per volume. Yeah, the volume of water is that you can drain from this volume of aquifer here. So basically, so the specific storage it has a dimension of 1 over L, and then this will make it dimensionless, and this guy is dimensionless. Okay, so now let's look at this into more detail. Okay, so here this is the specific storage. So now this is you got like a big overview. So specific storage, let's read what a specific storage is. Specific storage, this is the water volume released from or taking into storage. So that's like could be also released, like you can it's release or it's taken from like recharge per unit volume of an aquifer per unit change in head owing to compressibility. Okay, so let's see this. This is the water volume released from, like you release it from the aquifer, or you take it into storage, like you store it into the aquifer, any unit volume of an aquifer. So this is a unit volume of an aquifer. Yeah, okay. So I have like a unit volume of an aquifer. How much water can I compress then? Can I squeeze in this unit volume of the aquifer? This is basically what it means. How much water I can squeeze in or squeeze out, like remove, yeah, from the aquifer per unit change of head, like per delta H per unit change of head owing to compressibility. So how would I put it in? I will put it in by squeezing it, by compressing the water more. How will I get it out? I will getting it out by de-squeezing it, by releasing the water from pressure, and then the water will expand. Okay, and this has like two terms to it, yeah. So the total so this basically occurs like this compressibility, this the total load of the aquifer. This is uh, uh, you have like a total load on the aquifer, yeah. So you have like a total load on the aquifer. That would be the confining unit on the top of it. So like this confining unit here and this confining unit here, whatever above it to the land until the land surface. This is causing like a load, like a big load on the aquifers. That's for the unconfined aquifer. For the for the confined aquifer. For the unconfined aquifer, there is also a load, which is the load of the water above it and the air pressure. But that's not a big load as big as the load from like geological material above it, like and all this sediment and geological material above it. So the load of the aquifer that and then so that's on one direction. So on one like remember like Newton law, like balance of force. So if from one thing you have like this load above it, yeah, so you have like this load above it, and then what would be the opposite force or like the opposite load? So the opposite load, that would be the support that you will be getting from the rock matrix and the water, yeah. So like, and once this load increase, then you will start like have compressibility, and once this load decrease, then you will start to have expansion, yeah. So if these two loads are equal, like the load of the above, what is above like your aquifer is equal to the support through the rock matrix and water, then no change will happen. But if this is larger, then the water will, the matrix and the water will be compressed. Yeah. So, so based on like elasticity, like any increase in pressure, the material skeleton expand, and decrease in pressure, the mineral skeleton contract. Yeah. So that's basically what will happen, yeah. like so the increase in pressure, the water will contract, and the decrease in pressure, the water will expand. So if I increase the pressure, then the water will get compressed. If I decrease the pressure, how do I decrease the pressure? Through pumping, for example. The water will be expanded. So decrease in head, like if I have a decrease in head, the skeleton compress, and that like reduce the effective porosity and will expel the water. So the pore water will expand due to lower pressure. That basically what will happen. That's the mechanism. So like if you increase, like you decrease the head, the skeleton will compress, and then that will reduce the effective porosity, and that will expel the water, and the pore water will expand like due to lower pressure. So that in a confined aquifer, head may decline, yet the potentiometric surface will remain above the confined unit. In other, like, what does this mean? This means that, like, although water is released from storage, the aquifer remains saturated because I'm just releasing the compressed water. Yeah, and that's basically like this basically So basically, that's basically is telling you like this is specific storage. What does it mean? So it should have a unit of 1 over L. What does this mean? It tells you basically how much volume of water will come out from 1 meter of an aquifer, for example, if I lower the head by 1 meter. Yeah. So here, like I have 1 meter of aquifer, for example. Right? If I lower the head by 1 meter, so I lower, like, remember, like this is your original potentiometric surface, and then once you start pumping, you will lower the head there. So if I lower the head by, oops, yeah, you'll start lowering that. If I lower the head by like 1 meter, and this I have 1 meter cube of aquifer, how much water, like what would be the volume of water? So maybe like this is 1 meter cube of an aquifer. Yeah, this is 1 meter cube of an aquifer, and this would be maybe that. So by dropping the head by 1 meter, I expand maybe this much of water. Yeah. So from this 1 meter of an aquifer. Okay. Uh, from the aquifer. So here, like, so now, uh, how much water will come out if we lower the head by 1 unit? We are not taking water by gravity and draining the sand, like, and draining the aquifer material, like dewatering the boreholes. No, we are not lowering the water table, or there's no water table here. It wouldn't be cold water table. It's like cold water level. We are just removing pressure so that the aquifer skeleton compress and slight expansion of water will occur. And once the slight, and that's all what will happen. Like the skeleton will compress and the water will expand, and you will get it out. So you get a cone of depression in the, so as we see so in the previous slide, you get a cone of depression in the potentiometric surface, not due to lowering the water table, but due to reduction in pressure. Like, do you remember? We saw this in the previous slides. Let, let me show you this again so that you would remember what we were talking about. Here we go. So do you remember this? So this is your aquifer. This is your water level here. So once you start pumping, the water level here will not change because you are, oops, because you are not dewatering the pore space. You are just releasing water from pressure. So after you start pumping, what will happen is this potentiometric surface will drop, but this water level will stay the same. Yeah. And we have an equation for this. So let's look at if we want to quantify this. Where is that? Aquifer storage. Okay. So here basically that's like how you can quantify this. This is the density of the water. This is the acceleration due to gravity here. So this will depend on what? Like this will depend on the compressibility of the aquifer skeleton. So 1 over force over area, so that is like is compressibility of the aquifer skeleton. That would depend on porosity. Yeah. So that would depend on like porosity, and that would depend on the compressibility of the water. So that's basically storage. It depends on like two, like how you can compress the aquifer skeleton and how you can compress water. So different material will have different compressibility, and water generally will have like similar compressibility. It could be a little bit a function of uh, so water compressibility would be more or less like similar, will not change, but different aquifer skeleton will have different compressibility. Uh, but water is not does not occur like so. Water is not everywhere here. Water only in the pore space. So you need to account for porosity, like where water exists. Yeah. And that basically, like if you do this and you do your dimensional analysis, you'll get the specific storage something in like a unit of 1 over L. All right. So here is the specific storage value for different formation are largely very small. So this is like specific storage. Remember, like here, specific storage, it has a dimension of 1 over L. That would be like this is here. This is compressibility specific storage of water. Yeah, or like you can think of it like as a specific like uh, specific storage, or like as you can think of this number as like as a compressibility of water. So here, like this part, will be the compressibility of water multiplied by G multiplied by rho water. So if you did this, you will get like this a small number. But here for most rock, like you see here, gravel and densely sand, they don't have they have a lower compressibility compared to, for example, like clay. Yeah, like if you see like here, clay have a higher, sorry, specific, not compressibility, specific storage. So you see like it's a specific storage of sand, and gravel is less than of clay and silt. So for example, like let me read this for you. The specific storage of gravel is 1 part in, this means like the specific is this, what does this, like I'm telling you, what does this number mean? The specific storage of gravel is 1 part in 1,000 change volume per change in 1 meter head. So like let's say let me give it to you an example. Like let's say gravel, for example, S of gravel is 1 to the power minus 4. This means what? This means that it's 1 part in 10,000 parts. So let's say I have this 10,000, for example, like meter cube of an aquifer space. If I drop the head by one, if I drop the head by 1 meter, I will release from this aquifer 1 meter cube of water. I will release 1 meter. So this is 1 meter cube of water. I will release like 1 meter cube of water per 10,000 meter of like aquifer volume per 1 meter like drop in head in H in my head. Okay, so if I for each 1 meter drop in head, I will release 1 meter of water from this volume of an aquifer. So for sand, it is 1 part in. So for sand, it is like see, it's like a little bit, it's a little bit bigger. You can release like so for sand, for example, it would be like this. Yeah, for sand, it would be like every like one meet 1000 meter cube of water, I can release 1 meter of water. So for sand, it is 1 part in 10 over 3. That is 10 times more specific storage than gravel, which means it is softer, basically. Because sand is like softer than gravel, so you can compress it more, and then you can have uh, uh, more like storage of water. Yeah, the compressibility of water is much smaller than sand and gravel. So basically, like the compressibility of water, it is much smaller. Like if you compare here, it would be like much smaller than sand and gravel, which is something you might not expect. You might expect that gravel might have a higher compressibility than water. Okay, so now let's look at what does like for confined aquifer water is released due to compressibility. That is a specific storage. So in a confined aquifer, remember this is our storage coefficient, and it has two components. It has specific yield and it has a specific storage time your aquifer thickness, and this is like dimensionless. So in a confined aquifer, although water is released from storage, aquifer remain unsaturated. What does the aquifer remain unsaturated mean? Means that this one is be equal to zero. I'm not dewatering the pore space. So here, this is my original potentiometric surface, and now once I start pumping, this is a drop in my head. So here, this is the drop in my head, like this is my delta H, and then the cone of depression, and basically the storage in a confined aquifer, this is equal to zero, so this guy would be equal to zero. So storage and like storativity or storage coefficient in a confined aquifer, it is like uh, your like your aquifer thickness, like your saturated thickness, times the specific storage. And specific storage is given in this term. So that depend on the compressibility of the water, which is generally constant, and compressibility of your aquifer material like sand, gravel, clay. So basically, like the higher like sand has a higher compressibility than gravel, so sand will have a higher storage coefficient than gravel. And we've seen this, like the sand could be like 10 times more S storage coefficient or storativity than more like sand, like we've seen sand 10 times more than gravel. Yeah. Sand 10 times more storativity. So this is called like storativity or storage coefficient. This is a specific storage and this is a specific yield. So in so here in unconfined aquifer, no physical dewatering involved. Like in a confined aquifer, the head may decline as the potentiometric surface remain above the confining unit. See, you see here your potentiometric surface, it will remain above the confining unit. In other words, the aquifer remains saturated, so no physical dewatering is involved. That's the most important thing you need to understand here. Okay. Now, for a confined aquifer, that's a little bit different, yeah. So the confined aquifer water is mainly released due to physical dewatering. That is a specific yield. So in an unconfined aquifer, level of saturation rise and fall with the change in the amount of water in storage. So here, the main mechanism, like remember, like this sand column experiment, so I have a sand column here, I have a screen here, I open the screen and I let it dewater. So some of the, like you see here, it was fully saturated. Now it's not fully saturated. Now this is just like solid and air. Like here, this was like solid phase and water. Now this is solid and air, and this part is solid and water. What does this mean? There's actual dewatering, yeah? So in an unconfined aquifer, level of saturation rise and fall. So the main mechanism for storage or storativity, so this is the storativity, remember it's dimensionless, or storage mechanism in a unconfined aquifer is a specific yield. Do we have this one? Yes, we have this one, because remember, remember the pressure, like here, like this is my aquifer, for example. Like, see, your pressure will keep increasing. Remember pressure rho g h. Uh, so your or head here, like pressure head, like rho g h, it will keep increasing because you have bigger like water column sitting on the top of it, and above this water column you have a big air column. So you have an air column, and below this air column you have like water column. So you get like your pressure head like rho gh, and as you go down, like the water will get compressed, but that would be very small. Like, so the compressibility of the aquifer, like the aquifer matrix or the aquifer or the water due to the column of water above it as you go deeper and deeper, that would be very small compared to specific yield. So SY is order of magnitude larger than SS. Yeah, so that's like order of magnitude larger. For an unconfined aquifer, this guy ranges from this one. Remember, like this guy has a range of what? Like 10 to the power minus 3, or like 10 to the power minus 6 to 10 to the power minus 3, versus this one is like in the order of like, yeah, 10 to the power minus 2 to 10 to the power minus 1. So this is like at least 1 or 2 order of magnitude larger than this one. So if you assume that, like for a confined aquifer, you can assume that there is still like some compressibility, but not much, due to water column and air column, but not much. So you can assume that specific yield is much larger than specific storage, and therefore the storage in unconfined aquifer would be mainly due to specific yield. So this is your storativity, or your storage coefficient. So we call this a storativity or storage coefficient. In the unconfined aquifer, it will be specific yield. So let's look at this equation again. So my main storage mechanism in a confined aquifer, it will be through specific storage. So I will have this equation. My main storage mechanism in an unconfined aquifer, it will be through specific yield. So I will have like this equation. Okay, simple and easy. Uh, and then, yes, okay, so let's move forward. So we can calculate the volume of water drained from an aquifer as the head drops. So the amount drained for a decline in H in the head. So this can be calculated, like what is the amount drained from a unit decline of H. So this is basically the, like, let me write it again how we had it before. So the way we had it before, I'm just rewriting it, so I will tell you what we are calculating. So this is the volume of water over the area over delta H. Let's see this picture. So this would be my area here. So that's my area here. Let me remove this. Yeah. Let me just show you like this equation that we had. Yeah. Specific yield. Remember, like we have the specific yield as the volume of water over area over delta H, which is equal to this guy. So giving this one, this would be my area here. So that's the area. That would be the delta H, and that would be the volume of water that's drained. And if you divide it like these two, that will give you the specific yield, which is almost approximately equal to your storage coefficient for a confined aquifer. So I can rewrite it in this way, like I want to see how much water I was able to extract, or how much water I was able to add, recharge, because remember, like you can extract or you can also recharge your aquifer. So volume of water drained or added, that is equal to the storativity of my aquifer, yeah, surface area overlying the drained water. We looked at this one, like this is the surface area, and average decline in head. We also looked at this one here. Yeah. So let's look at example. Yeah. Discard. No, I don't want to do this. Oops. What's happening? Uh, let's look at an example. Okay. So example, like let's look at this example. So try to do this example, and then we can look at the solution uh, together. Or let's just, I mean, how about this? Like pause the video, yeah? We will solve it together, but I want you to pause the video, try to solve it on your own. So pause the video, try to solve it on your own, and then we can do it together, yeah? Uh, so you have like, for example, an unconfined aquifer, its area, so that is like the area is a mile. The water level declined by feet. So now you see here. Oops, no, don't look at this one. Let's solve it. So here, that's the area. So area is given. You need a confined aquifer has this area. Water level declined by this one, and the confined aquifer specific yield. So this is the specific yield. And I will like so you can get like this specific yield, like you can get it from tables, or usually we also estimate this is specific yield in model through model calibration. So one of the usually is a parameter when I develop like a groundwater model, what one of my calibration parameter is almost a specific yield. I know a range from it, but I don't know the exact value for this aquifer. So I know, for example, uh, for sand and gravel, it should be from this range. For gravel, it should be from this range. For sand, it's from this range. From fine sand, it should be from this range. But I don't know the exact value. So, uh, because remember, like I showed you, like we had, remember, we know these ranges before. If you remember it, let me show you where we get like this specific yield from. We've seen this before. Let me show you an example here. Mhm. You remember something like this? Yeah. Hydraulic conductivity. Yeah. Specific yield. So you remember like the specific yield like for different material for clay, silt, sand, and gravel. So we know something like this here. Okay, so here, but we generally calibrate this from the model. Okay, unconfined has a specific yield of this. Confined aquifer, so like has a specific storage of this one. So the specific yield, it has like this is unconfined aquifer, an unconfined area is the water level of this storativity like that. So let's assume that you have an unconfined aquifer, it has a specific yield of this, and you have a specific storage of this. How much water was lost from storage? So this is like aquifer area, like you can just say like an confined, like an aquifer area. So because we will do it for both, yeah, an aquifer area has this much, so water level declined by this much. So let's assume if this was an unconfined aquifer with this specific yield, or this was a confined aquifer with this specific storage, or like both of them, like specific storage time S, that will give you time the aquifer thickness. So this would be S here also, yeah. How much water was lost from storage? So how to solve this? So remember we have the water that's lost from storage. That would be the storage coefficient time H time area time delta H. Yeah. So you can substitute like this guy here, for example. You need to convert this from mile to feet, so you can do this. So you convert this from mile to feet, and then you sub. This is like your delta H here. That's your delta H, and that's your S here. So this is the S for the unconfined, and this is for the confined. So if you did this, you will get something that looks like this. Yeah. Uh, you get something that looks like this. And the same drop, yeah. So the same drop in the head in a confined aquifer, like with this S, you get something that looks like this. So you see here, six order of magnitude larger. Like you can get water like six order of magnitude larger from a unconfined aquifer, like from an unconfined aquifer versus like a confined like aquifer. Okay. Let's look at another example. I think this is the last slide. Let's see how we are doing in time. Hope this is not getting long. Yeah. Let's do another example. Uh, so the figure above plots the depth of a sensor below water level. This is actual data from Floridian aquifer. So the figure above plots depth of a sensor below water level in a well drained into the Floridian aquifer. So at Florida State University, they have a deep well that tap deep monitoring well that's monitoring the Floridian aquifer, and this is data that you are getting. So this is like time data, and this is change in hydraulic head. Yeah. So the figure indicates the hydraulic head in the confined aquifer increased by about over 1 week. So that's like 1 week of data. And you see like over 1 week, what is delta H? You can, oops. So over 1 week of data, yeah. So this is like in 1 week. So what is delta H? So delta H, that would be like 10 to the power 3, 5 minus 10 to the power 2. So that is like 0.015 meter over like 1 week. If we assume that the storage coefficient, storativity of the aquifer, so if we assume that the Floridian aquifer, uh, the storage coefficient of the Floridian aquifer, so is storativity or storage coefficient is 0.005. Yeah. If that is the storage coefficient of and the head change at this well is representative of Leon County. So Florida State University says Leon County. How much water was stored in the aquifer for the county for over a week? As use the county size. So if this is the county size, if this is how big Leon County is, Leon County, this like Leon County is this where the Tallahassee, the state capital, is, in case you don't know. And that's where like Florida State University is. There's also FAMU, like Florida Agriculture and Mechanical University, FAMU. So you have two of Florida University are there. So how much water was stored? So there is a change in head is positive. So this means you are not removing water from storage. You are adding water from storage. So how much water was added? You can easily calculate this. You have your storage coefficient, you have the area, and then you have delta H. So if you did this, you need to convert like a mile to a meter. So you get about like not bad. I mean that's a lot of water. Yeah. 36 million gallon of water was added over a week. Yeah. So that's how much water was added to this Floridian aquifer over a week. Okay. So I think that's all for this video. Yeah. And I will see you in I think, yeah, no. Sorry. That's not all for this video. So I will end here. I want you, I know like this is one of the uh, this course is easy, yes, not difficult. But one of the like parts that you need to practice for this course is just like you know the difference between these terms. Yeah. So what I want you to do, and this is why do you need to know these terms? Because that's how you will develop your engineering sense and your basic and fundamental knowledge. And you will see that all these things will be very useful when we go to the applied part. So the first part of this course is the foundational knowledge and like conceptual knowledge and foundational skills. So basically, you will see that this conceptual knowledge is very important when we get to the applied part, like the field, like how to do field uh, field work, like how to do like field measurements and how to use this field measurement to develop a groundwater flow model. You will see all these things coming through. Like you'll see that, okay, for our groundwater models that we need to calibrate, we need to find the hydraulic conductivity. We need to find like specific storage, for example. We need to know like transitivity, things like that, yeah? Or you will see that how these will become very useful to know. So I want you, if you don't know these terms, please go check what's the meaning of permeability. So permeability, this is a property of like the porous material. So I want you to check what's the meaning of this. Property of porous material and fluid, that would be like hydraulic conductivity and specific storage, yeah? Because this has to do, like, remember this specific storage for it has to do with the compressibility, like the specific storage of if this borehole was filled with oil, it would be very different than if it was filled with water. So this is a property of the porous material and the fluid. And you saw sand, gravel, oil, water, each one has its own like a specific storage. Property of an aquifer layer with thickness. So that is a property of an aquifer layer with thickness. That would be like transmissivity, which is like hydraulic conductivity times B, and that would be storativity, is such as like, for example, a specific storage time B. So I want you, so this is just a summary for what we have done so far. So please go check, make sure that you understand every and each this one very carefully and clearly. Okay, so that's all for this video, and I will see you